Coming up next is Sarvesh Kumar Malladi from Universal Robots. He'd be speaking on the development of ROS2 within the Universal Robots ecosystem and would be introducing you guys to the ROS2 features that UR offers and how it's making it easier for researchers to transfer or transform their products into the industry. On to you.
All right. Yes. Namaskara, Bengaluru. Thank you for having me at this vibrant conference. My name is, well, my slides are not up yet. There you go. Yeah, my name is Sarvesh Kumar Malladi, and I'm part of the team at Universal Robots that deal with connectivity and safety. This also encompasses the development and integration of ROS2 within the UR ecosystem and the UR robots. And that's what I'd like to share with you as our story and our journey on how we went about integrating ROS2 and some of the challenges we faced and maybe even the status of the new features that has come up with ROS2 with UR. So as as every story goes, there's a protagonist and we like to call him a robot. We describe him with different adjectives, and some of them are easy to use, user-friendly, expandable, and integrable, easy to integrate. And what this has is a lot of advantages and use cases, but also disadvantages where you have a plethora of features being developed constantly, and this can overwhelm the developer when they keep getting a new feature every other day. Then it's hard to keep up. So you need a industry standard interface to encompass all of this and be able to use all these features. Along with it, we don't have features like QoS or multi-robot control, which are quite important for Industry 4.0. So all these problems, and then what's the one solution? Well, obviously ROS. That's why I'm over here talking about it. So challenge number one is to integrate the UR into the ROS network. And this often the simplest solution is the best solution. And what you do is just write a driver or mediator between the two interfaces. So that's what we did. We have a ROS main node. This can be your application for the camera or actuator or whatever it is, which has to integrate with the ROS2 driver. This is, of course, over ROS. The ROS2 driver is written on something called the UR client library, which has a few of the features that were listed from earlier, like primary, RTDE, and dashboard. What this essentially means is these are protocols or features that help you interact with the robot over TCP and IP. So you can send scripts to control the robot and get the necessary data to diagnose it or to have a loop or a feedback. And that's how the whole loop works with the ROS2 driver. When you have two controllers running, now it would be the ROS controller and the UR controller. Often there's a question that arises, which one has to take command or which features do you use? Well, be selfish, use both, right? ROS is known for its state machine and trajectory controls, whereas on UR, we have our own proprietary technology for using the robot with an intuitive interface, right? Like I'll talk about a few of the interfaces that we developed. So it's exposed to ROS2. And that was the idea, was to write some of these features in ROS2 so you can use it via these interfaces rather than the teach pendant on the robot. So the first one, scale trajectory controller, which is basically to send forward speed reductions to the robot. This can be because the user needs the robot to go at a lower speed, or the safety feature or plugin needs the robot to slow down for whatever reason, right? Maybe someone entered the protective fence or something like that. So this has also expanded now to the JTC, the Joint Trajectory Controller, which was already a service implemented. Brief thing about JTC is it essentially interoperates the between the waypoints. So it embeds the information of the path, the velocity, and now even speed reductions. There's no interface change for the JTC. The service still accepts the same parameters, but now it also has the speed reduction embedded into it. What's wrong? There you go. Another cool feature is free drive. The video is supposed to be playing, so in words, I'll try to explain what free drive is you can move the robot quite freely without any brakes operated. So this helps you move the robot to a new position and then teach that position for your programming. And this is easier to use than, let's say, jogging the robot in Cartesian space or TCP space, which might not be the most intuitive thing. In the obvious sense, this has to be integrated as a service, but there's a reason we integrated it as a topic. So it's essentially a topic that's publishing. The free drive is the topic, and then you're publishing the messages of whether you're activating or deactivating it. And that's because you can use free drive on the teach pendant. And when you use it on the teach pendant, that has to take over the entire system for safety ratings and safety standards. So and a topic is interruptible, but a service might not be the most the logical one to be using there. Another cool feature, force drive or force mode. So you can define an active force in a Cartesian space and the trajectory. So popular applications for this is polishing, sanding, and this again is a service with options to even include the damping coefficients. So you can include your own controller to control the force mode when you're using the robot. Yeah, so ROS, as everyone knows and everyone's been talking, it's popular with the simulation environment. I'm not going to go into much details about this because you will hear a lot more talks relating to this, but we have supports for Gazebo, URDF files, and out-of-the-box simulations that you can play around with. We also, for someone who needs it with less resource overhead, or you don't need a GUI, but you just need a mock hardware, for writing integration tests or something like that. We have a mock hardware where you can test your kinematics and even I/O simulations within this. And Isaac Sim. Okay, that's Isaac Sim. NVIDIA, the person at NVIDIA just spoke about it in quite length. NVIDIA also supports it has full support for the UR simulation. So you can run your reinforcement learnings and training models on Isaac with URs and renderings in it as well. So challenge one was to get UR on ROS network. You've achieved this. You have advantages, of course. You can use your own ROS network. You can use it in all the current robots on the market. And it's just exposed to it now. But you have challenges now. So challenge number one is, since the communication with the robot is done through TCP/IP, you have a latency overhead. You need to come across this because you can't use it in real time or else. Which brings me to point number two. ROS does not guarantee real-timeness on robot operations, whereas we have our own programming language called the UR script, which guarantees that on the robot. So how do you use this feature on ROS, right? How do you need both. You need a real-time application on the robot. Third one is GUI. The GUI, the Polyscope X, that's the new Polyscope version, is on TypeScript. How do you use ROS features on the GUI? Because you can't expect every machine operator to be quite well versed with engineering standards, right? Like you guys would be comfortable with using ROS, but someone who's on the factory floor might not be that comfortable with ROS. So you need a GUI interface to make it easier for them to use. So 3 problems, 1 solution, like the shampoo ad says, right? Integrate ROS into the robot. So in this case, the robot acts as a ROS node. We have something called the URCap X or URCaps. That's the plugins for the robot, where you write your own applications and solutions. And if you were to do that with a ROS driver, then it's going to be another hurdle for you to translate that to ROS. But now it would be all on the same environment, so it's quite easy for you to use. So you have your internal URCaps. These are usually, we use this for industrial protocols. And you still can use the ROS driver because we have features built for it. We don't want to get rid of them because they're good features. So all of them can be integrated into one smooth platform. So if you remember the beginning slides where ROS was used to integrate all the external features of the robot, we have a lot of inner moving parts as well. So we decided to use ROS to even unify these internal moving parts. So you would have a common ROS to message bus running below. Then you have a Polyscope X, that's the GUI. UR X, that's the plugins that you write with either sensors or actuators that you want. Again, you have off-the-shelf ROS devices, again, sensors and actuators, which are getting more and more popular now with the growing community. You can use that, and the coolest feature, cobot fleet or multi-robot operations. You can do all this when you have a common ROS message bus line, and you don't have any other hurdles to deal with, rather than just write your application and go straight into it. All of these are, again, Dockerized, containerized, so you have a very clean environment and easy setup to go for. So coming back to UR script, so we have two interfaces on the robot, like any other robot. You have the GUI, but what's under the hood or under the GUI is the UR script. So this is a programming script or language that we designed within UR, which guarantees real-timeness, real-time performance. And just like any other programming language, you have variables, types, and loops, all these functions available. But along with it, you have some pre-built functions like I/O control and field bus controls like Profinet, Ethernet, IPs. You have functions for that where you can just plug it and use it on your script. And of course, robot movements. That's the obvious one that's there. But here we faced another challenge. So UR script is interpreted with CPP. So it's essentially compiled down to its own bytecode. When that happens, how are you going to integrate, or how are you going to communicate with custom ROS types or ROS types, like ROS message types, service types? How do you do this at compile time? This was one issue that we had, because we can't have a restrictive solution where you just have a set of ROS message types and you only use that because user wants to make their own ROS message types, custom ROS types, let's just call that. So what we came up with was to rewrite RCL-CPP. We wrote a version of RCL-CPP internally such that you can have this custom ROS types in your Polyscope X or the UR X. So you can create your own message types and then very seamlessly integrate them into the UR script and then write your applications and play around with them. So this is just an example. I won't go into much detail, but this is how your ROS would look on your UR script on the GUI, right? So you would have your subscriber factory, which takes the same parameters as your normal subscriber, a name and a message type. You have two read methods. This is from the QoS. You have a read and a read history, where read reads the current message that's coming on the topic, and read history reads the last n messages on the topic. So one guarantees the real-time performance, but you might have a data loss, you might have package losses because of network load or whatever it could be. And on the other hand, you can read the last n messages where you guarantee that you don't have any package losses, but this is not. This is going to fall behind on real-time performance. And what we observed was also that read acts as a blocking call. So when you have a read going on, and let's say it doesn't get the package at once and it stops, then it stops all the operations. The movement of the robot and everything would essentially stop. So we had to deal with that. So that's why we call it a blocking call and a non-blocking call between read and read history. Publisher, similar to subscriber, the name and the message type. And we found that the best data type to deal with ROS was structs. So we introduced a struct, which is similar to the CPP struct. So you have named parameters. You can have complexities within that, where you have a struct of structs, struct of poses, struct of strings. I don't know, go nuts with it, right? You can have any of those complexities inside. We also have services and actions included in that. And the return type of the service is essentially two structs, result and the reply. A result is a struct with a Boolean, which tells you whether it succeeded or failed, and a reply struct, which is the actual data from the service call that you do. So all of this now, when you integrate it, how would this look for you as a user when you use the robot? So you need to make a UR-Cap X, which is in simple terms a plugin for your own application. You would have your own ROS driver, which could be your actuator or your sensor. You have a ROS2 driver for that, which is encompassed in a ROS2 node to be able to easily identify it from any other device on the network. And this should be running in a Docker image, so you have a clean environment. Then you have a TypeScript front-end on the UR-CapX package, which makes it easier to interact with the Polyscope's Polyscope as in the UR software or the UR GUI. And remember how we rewrote the RCL-CPP? Well, now you can have custom ROS types, so you can write any application through ROS and be able to interact with the robot. This, in the overall frame, falls under this image, or let's say the structure, right? You have your UR-CapX that has to interact with the controller. The controller has its own custom ROS types and some topics that it's publishing and subscribing to. We unified it with the ROS2 message bus, as I mentioned before, so everything is seamlessly communicating over this message bus line. And the TypeScript front end, there was the challenge of translating ROS to the TypeScript, so you could use it on GUI. When you take a teach pendant, you can just choose the ROS types and ROS features, and we have a ROS2 bridge that translates it to the GUI, so everything is seamlessly integrated into one solution and easy for you to play around with and explore. Okay, the videos aren't playing. Yeah, so we ran some experiments with the integrated ROS to see its performance versus a ROS2 bridge and a ROS2 driver. So videos were supposed to be shown, like the first video shows a one-to-one mapping of a robot master-slave combination where one knows where it's going, the other one tries to follow close to each other. Second one was where the master robot publishes its 3 positions that it's going to, and the kinematic solution for the slave robot is essentially it calculates it on its own. So you can see the 2 robots going to the same points but with different trajectories. And the last one was free drive enabled on the master and the other one trying to closely follow, where you can still see a little bit of a lag. And that lag was due to the second robot, rather than trying to follow the points as is, it tries to find a solution to these points. So it's doing an inverse kinematics every time it tries to go to these points. So that was an interesting thing that we had to deal with. Well, we've successfully integrated ROS2 into Polyscope or the UR, but we still have some challenges. One was backwards compatibility, and as I've seen over the talks, that a lot of them have not moved over from ROS to ROS2, and this is a common thing in the industry where they don't switch over as quickly as, let's say, a research group. A research group is quite flexible in trying to get the newest ROS out there, but the industry would be like, yeah, let's hold back a little. Let's see if we really need to, migrate to the new ones. In that case, backwards compatibility is a very important aspect of it, and we've noticed a few challenges when we use 2 different ROS versions. For example, Foxy and Iron, and we noticed there were some performance issues when we used services and actions. So that's one challenge. Challenge 2, integrating with industrial protocols like Profinet, Ethernet IP. While Siemens and Bosch have stepped into it and started translating these industrial protocols to ROS to be able to use them seamlessly, we still need something internally for users that do not want to switch to ROS or want to switch to ROS, but they don't want to switch their Polyscope version or the robot. They don't want to invest in a new robot just for them to be able to use this one feature. And high traffic load, but there's a talk again on the Zeno, so that again deals with this issue of it. We still have to experiment with that within the company, so fingers crossed that they solve the issue of these high traffic loads. So, conclusion, in simple terms, we have a ROS2 driver. You can use that with any of the current UR robots. We seamlessly integrated it with the new Polyscope version. If you scan the QR code, you'd be able to get details of this Polyscope X and when the release is and how you can get it onto your robot. A unified communication interface with ROS. We've experimented with that, implemented that, and we're quite happy with it, I would say. And we will also have ROS support in our programming script, the UR script. That's it. That's my time. Thank you.
Thank you, Sarvesh, for the talk. We do have time for 2 quick questions. So, if anybody from the audience, can we have a raise of hands, please?
Yeah, hello.
Hi.
Yeah, can you please expand on what do you mean by providing a real-time guarantees using UR script? Because ROS itself doesn't provide any guarantees for real-time message delivery, right?
Yes, and that was precisely the reason why we integrated the tool, because UR script, the whole binary or the whole program is written in such a way that you have some protocols that should not be interrupted, some robot motions, some safety protocols, all of these were taken into consideration on how we write our binary. And UR script, of course, knows that because it's a direct link to the binary. And if you use a feature, so as simple as, let's say you have a move command, a move J command, and then you have a safety feature from a PLC or a fence that interrupts you. We know in UR script through testing and through the programs that we have written that it is immediately stopped. This again cannot be guaranteed. I say it cannot be guaranteed because you can still achieve this in ROS, but it's not guaranteed in ROS that you have your safety signals getting through immediately. And that's what I meant by UR script guarantees real-time performance, because we've written it with those parameters in mind.
Hello, sir. Thank you for the talk.
Yeah.
I'm a student of IIT Kanpur. Actually, in my lab, one of our seniors has worked on this. He has published a paper where he was using a UR5 manipulator,
Okay.
wherein he was trying to the problem statement involved picking objects. Like there are a set of objects that are arranged in a proper order, and then the manipulator goes on to pick up the object which is closer based on the depth information from the camera, and also not at the same time not disturbing the already arranged objects that are there. So
Okay.
with respect to the improvements that have been there with integrating of ROS2, what are the improvements in perception and image processing stack? Could you throw some light on that?
The direct one I would say is the lag. So I don't know if you face the same thing when you use a ROS2 driver. There's a lag between the communication of the, let's say, like the camera publishes a pose and the robot has to recognize the pose and then manipulate or move to that, right? So there was a delay in how you got that information. So that is that's been taken care of.
Mm-hmm.
The other advantage is, as engineers, for you, I think this would not be a very major advantage as in for using the internal protocols like this UR caps and GUI, right? So these parts of integration, the UR caps and GUI, is mainly for people who are not engineers, like they don't know about programming languages and things like that.
Yes.
But now, actually, there's one thing you could do with the UR script. If you implement your solution in UR script, then, as I mentioned earlier, you can have real-time performance. So you can include safety parameters and any other, like even improve the performance of your already existing application with these features. So that would be an advantage for you as well.
Thank you so much.
Hi, Sarvesh. Thank you for the amazing talk. So like I am from TCS Research in Bangalore, and we have two UR5 E series and one UR10. We have been using ROS drivers for a long time now,
Mhm.
and even the one in ROS2. So I have this question that when we are using custom grippers on top of URs, so what is the kind of support that UR driver is providing to integrate the gripper libraries along with the like to bring them into the ROS framework? Like there is, of course, the support from the gripper side is required, but as the grippers are usually connected through the UR's Modbus or other systems, can you share some information on this?
So the grippers are usually implemented with what I said, the plugins, the URCap X.
Yeah.
So that's the direct interface that we provide for you to control the grippers. Now, if the gripper on its own has a ROS driver, let's say you're using ROS2 driver from your application to the robot, and then the gripper has its own ROS2 driver, then you essentially wouldn't use this URCap X, because then you wouldn't use Modbus or anything. You would have a direct communication with that. But if you want to use it via the Modbus, so let's say you want the gripper and the robot to be one unit and communicate through that, then I would say use the UR script.
Okay.
So those will have any of the UR caps that's built for the grippers. They would have these features already available in UR cap in the UR script for opening, closing, or operation of the grippers. So you can use that through the ROS driver then.
Okay. Thank you.
Yeah.
Yeah, thank you very much for the wonderful talk. So my question is like, you told that there is a lag between the data that has been captured from the camera. So the first question is that whether the lag still continues with any other sensors or the actuators that you connect to the system, and whether the lag changes with respect to the other hardwares which you connect. So can you please throw the lights on which hardware exactly is being used, and what is exactly the lag with respect to the camera, and what is the lag with respect to any other sensors or the actuator that you connect?
Could you repeat? I'm a little confused. Sorry.
Okay, sorry. So you told that there is a lag in the data that has been captured from the camera,
Right.
right? So that lag will be still persist with the other sensors or the actuators that have been connected to the controller.
Mhm.
Maybe like, for example, the motors or any other encoders that you connect. And the second thing is that will that lag changes with respect to the controller which you use? Maybe if you're using Jetson kind of things or something else. So will
Okay.
this change or remains the same?
Okay, yeah. So the lag I mentioned wasn't inherently the sensor providing the data, but the interface. So when you, so let's say between the sensor and the controller you have ROS, and then within the ROS you use TCP/IP. So no matter how fast your application is running outside, at the end your weak link is TCP/IP. So there you're always going to have a little bit of a lag and a little bit of a delay. So that's the lag I was talking about. So outside you can use Jetson or any accelerator, but when you use a driver, then that's your weak link. And we got over that with the integration, so you won't have that issue.
Any more questions for Sarvesh, guys? We're good to close? Okay. Thank you so much, Sarvesh,
Thank
for
you.
the talk. Thank you.